As I said earlier that in the Lagrange's interpolation formalism, we could not improve the accuracy by including one more data point or extending our set by one more data point. The Lagrange's basis polynomials which we have described would have to be computed once again all over again from the start. In fact, these Newton's interpolation formula that we are going to describe now takes care of that difficulty. Okay. So, so we can take into account one more data point in our polynomial and can improve its accuracy. So, Newton's polynomial is so n stands for the order of the polynomial as I said earlier. This is the linear x independent term, then it is a linear term, and this is the quadratic term and so on, and we have all the way up to a n x minus x 0 and x minus x n minus 1. So, we have n data points starting from x 0 to x n minus 1, and we are going to construct a polynomial, nth order polynomial according to this, where a 0, a 1, a 2 are coefficients which have to be determined. So, the data points that you obtain, as I told you that these are the data points obtained from either a computer experiment or a real experiment. Suppose you are tabulating data for a very large class. This is from the perspectives of a teacher, that when he or she has gotten the marks for a particular course for a large class. So, there is a roll number versus the marks that one obtains, and then one makes a table out of it, and then one can actually find out the performance of the class from the data by doing certain analysis. So, whether we have really a normal distribution, I am going to describe that, or what is the full width at half maximum or the variance of a distribution and so on. Here we are simply talking about these are mostly monotonic functions, and even if they are non-monotonic, it does not matter. I mean, there are non-linear functions that we are anyway talking about, but even there could be points of inflection where there is a non-monotonicity. But in any case, we are talking about this polynomial and a set of data points. So, the data points are given by x 0, f 0, we call it f 0, which is a value of the function at x equal to x 0, and then you have a x 1, f 1, similar meaning goes, that is the value of the function at x equal to x 1 is called f 1, and similarly you have all the way up to x n minus 1, f n minus 1. So, these are the interpolating points. So, which says that P n at x k is some value of x, is called as f k, where k equal to 0, 1, 2 all the way up to n minus 1. So, at x equal to x 0, P n of x 0 equal to a 0, which is nothing but equal to f 0. So, at x equal to x 1, P n of x 1 equal to a 0 plus a 1 x minus x 0, that is a linear polynomial which we are going to call as f 1, and since your f0 is a0, we can simply write it as f0 plus a1 x minus x0, and this gives us a1 equal to f1 minus f0 divided by x1 minus x0, which is typically the slope. So, so far we have talked about the 0th order polynomial, which is a constant term, and we have talked about the linear polynomial, that is of the first order. So, we have at similarly then proceeding at x equal to x 2. I am doing this because you need to actually get all these coefficients in terms of these functions, and I guess showing up to a 2 would be enough. You can build up these other functions a 3, the coefficients a 3, a 4, etcetera, from the values of the functions. P n of x 2, it is equal to a 0 plus a 1 x 2 minus x 0 plus a 2 x 2 minus x 0 x 2 minus x 1 equal to f 2. So, that is the value of the function at x equal to x 2. So, if you put the values of a 0 and a 1, of course, a 0 is equal to f 0 and a 1 is what we have just obtained in terms of this, basically the slope which is f 1 minus f 0 divided by x 1 minus x 0. So, if you put both, then the a 2 comes out to be f 2 minus f 1 divided by x 2 minus x 1 minus f 1 minus f 0 divided by x 1 minus x 0 whole divided by. So, let us just write the left hand side a little carefully. So, this is a 2 and this is x 2 minus x 0. Okay. So, we define slightly cryptic, may not be easier, but for our convenience we use these notations. We call it f x, we write it in square bracket x k plus 1, because you see always we are talking about the difference in the functions, values of the functions at 2 points. So, this we can call it as f x k plus 1 minus f of x k divided by x k plus 1 minus x k. So, with f of x k denoted by f k, we can write down another function which is of a larger, just like your a 2, which involves 3 functions, the values of the functions at 3 points, namely f 1, f 2 and f 0. We can define these functions as x k plus 1, just like x 0, x 1 and x 2. So, it is x k plus 1 and x k plus 2 is simply like your, now this has to be written in square bracket, because we are writing these functions in I mean these values x k plus 1, which are data points, in the single bracket, but whenever we are defining these the left hand side, which is a function of 2 points, then we are writing it in square bracket. So, if that is the case, then we have a x k plus 1 and a x k plus 2 and f x k and x k plus 1, and this is like a x k plus 2 minus a x k. Okay. So, these are your notations that we have defined. This is for our convenience. Let us go ahead with these notation and define the most general one. So, that is f x k plus 1 going up to x I plus 1, that is f x k plus 1 going up to x I plus 1 minus of x k and going up to x I, and I have a difference in x I plus 1 minus x k. That is the two extreme points, the difference between the two extreme points. So, these are called as divided differences. Okay. So, these above equations okay. So, this is a new term that you have. So, it is called, they are called divided differences, these f functions. So, what we have in terms of our known quantities, that is these coefficients. So, our coefficients are like a 0, which is equal to f 0, which is nothing but f x 0. Then you have a 1, which is a f 1 minus f 0 divided by a x 1 minus x 0, which is nothing but a function of two things, which is x 0 and x 1. Similarly, a 2 is f 2 minus f 1 divided by x 2 minus x 1 minus f 1 minus f 0 divided by x 1 minus x 0. This is like x 2 minus x 0. So, let us again align to remove any confusion that you may have while working out. So, that is your a 2, which is nothing but equal to f of x 1 x 2 minus f of this has to be a square bracket x 1 and divided by x 2 minus x 0. Okay. So, I believe this is clear that we are trying to again talk about another polynomial, just like yesterday, or rather the last time that we talked about the Lagrange's polynomial. So, this is that Newton's interpolation polynomial, which uses this divided differences, and and you could figure it out that it is not a problem to include one more data point and improve the accuracy, because it just requires you to calculate these f functions once more. So, we have this can be written as so this is like a f and a x 0, x 1 and x 2. So, if I want a x 3 also to be included, I can write down a f x 0, x 1, x 2, x 3 by simply incorporating the divided difference in this particular fashion. So, the name is that. So, a 1 is called as the a 0 is of course, the 0th order divided difference, a 1 is called as the first divided difference, and a 2 is likewise the second divided difference. So, with this we can write down the Newton's, just use this word once again to make it very obvious that this is the divided difference method. Divided difference interpolating polynomial is written as P n x, that is f of x 0 plus f of x 0 x 1 x minus x 0, that is a linear term, and then we have a quadratic term, and this x minus x 0 into x minus x 1, and then we can continue, we can have a cubic term, which would simply have, if you want me to write this. So, there is a cubic term which would be simply x 0, x 1, x 2, x 3, and then you have a x minus x 0, x minus x 1 into x minus x 2, and so on. Okay. So, this plus if you carry on like this, then we will have a x 0, x 1 and so on, and a x n and x minus x 0, x minus x 1 all the way up to x minus x n minus 1. Okay. So, this is the procedure that we should follow. Now, you see that if you have suppose you need to do a quadratic interpolation, and in which case you may want to actually include 3, which is the minimum number of points that you should include in order to do a quadratic interpolation. But suppose you want to do include couple of more data points, that is 5 data points. You only need to calculate these f functions, the values of the f functions, and can calculate it, can improve your accuracy in the same program. So, the same program can be a little more can be added in order to calculate or including these 5 points to do a quadratic interpolation. So, this is written in a summation as I equal to 1 to n, and we have a f, and you have a x 0 all the way up till x I, and then we have a product of functions which is j equal to 0 to I minus 1 and x minus x j. So, this is the P n x, that is the so, this is called as the Newton's interpolation polynomial. Okay. So, this is what we need, and let us look at a simple problem again. So, example, table of log x is given. Okay. So, this is the table that you have. And okay, so you have these are labels for the serial number, then you have these values of x, and then log of x I. So, when I equal to, so this is the 0, this is the marker for the counter, rather the counter which counts the number of data points. So, it is 0, 1, 2, 3. So, there are 4 data points. If x I equal to 1, then of course, log of x I equal to 0, then it is 2, then it is 0.3010, and when it is 2, when it is 2, then it is equal to 3, and then it is 0.4771, and when it is 3, this is 4, and this is 0.6021. Okay. So, a number of x values have been given such as x equal to 1, 2, 3, 4 and the values the log of those x's are also tabulated. Now, what you have to do is that find log of 2.5 which is not given here, which lies between 2 and 3 doing a quadratic interpolation. Okay. So, quadratic interpolation, as we have told several times, that it requires 3 values. A linear interpolation needs 2 values. So, these 3 values can be any 3. If you wish to actually incorporate 1, 2 and 3, because 2.5 is subtended in that case, you can go ahead. I will include 0, 1 and 2 and do this quadratic interpolation such that the 2.5 actually lies beyond what we have taken and do a quadratic interpolation and get the value. Let us see. So, a 0 which is nothing but f at x 0 which is 0, okay, because your x 0 point is this. Your a 1 equal to f x 0 x 1 which is equal to f x 1 minus f x 0 divided by x 1 minus x 0 which is equal to 3010 divided by 2 minus 1, this is equal to 0.3010. So, this is the value of the slope which is 0.3010 which is calculated from this value of the function, which is of course, because the first term is 0. So, we get just 3010 and we have a 2 minus 1. All right. So, a 2 which is nothing but f x 0 x 1 and x 2, we have f of x 1 x 2 minus f of x 0 x 1 divided by, I am just following the definitions that have been given earlier. Now, f x 0 x 1 we have already calculated f 30 which is as a value 0.3010. Now, we need to calculate f x 1 x 2 which means it is f x 2 minus f x 1 divided by x 2 minus x 1. All these values are given here. So, we can use them and calculate this value, and then this value is already known, this is known, and one can get a value which is 0.4771. I am giving you up till 4 digits of accuracy. If you wish more, please go ahead. 3010 and this is like 3 minus x, sorry, this is x 2 minus x 1 because so this is x 2 minus x 0. So, now this is will just calculate it the intermediate such that so let us just calculate f x 1 x 2 which we have not calculated, the other one we have calculated. So, it is f x 2 minus f x 1 divided by x 2 minus x 1 which is equal to 0.4771 minus 3010 divided by 3 minus 2 which is equal to 0.1761. So, that is the value of this one here, that is the value of this one which we have calculated here, and this one is anyway the value that we have obtained here. Now, we have both the values. Now, we can go ahead and calculate A 2. So, A 2 becomes equal to 0.1761 minus 0.3010 divided by 3 minus 1 which is minus 0.606245. So, we can construct a quadratic polynomial using all our a 0, a 1 and a 2. Now, we know I am so sorry, a 1 has to be multiplied because that is a linear function. that has to be multiplied with a x linear in x term, and a 2 which is x minus x 0 and x minus x 1, and we will keep up to this. A 0 is of course 0, and this is 3 0 1 0, and this is x minus 1 plus this is 0.06245 into we have gone one digit more here, x minus x 1. So, x 1 is nothing but this value 2, and sorry, x minus x 0 is 1, x minus x 0 is 1, and x minus x 1 is 2. So, if you simplify this and then put x equal to 2.5, which is where you need the value of the algorithm, then you get a value which is 0.4047. Okay. You can check what the exact value is, and if you use a linear polynomial, that is, had you stopped at this a 0 plus a 1 x minus x 0, then you would have gotten a value which is 0.4515 for x equal to 2.5. Okay. So, you see that we are much better off by doing it has gone down by a by 0.05, which is a large number as far as the numerical accuracy goes, and quadratic gives you a value which is much better. Of course, that you would understand if you actually calculate the log 2.5. Now, the important point is the following, that as I told here, that if you want to include one more term, that is this term, that is which we have left out, which is 4, that is x 3. If you wanted to have a x 3, you simply had to write down or if you want to take into account 3 different terms, that is 1, 2 and 3, then you have to calculate the a 1, a 2 and a 3, and then you could simply do it by computing the divided difference these functions. So, this is mostly about curve fitting, but let me tell you on a general ground what we need about curve fitting. So, general features, of course, we could have told earlier, but we will talk about a few general features, and basically the mathematical preliminaries that we need for doing curve fitting of a set of data points that we have obtained from an experiment. But at the same time we need a few mathematical details that are needed, and because we are dealing with a very large number of data points, it is neither possible to show in the class by considering a large number of data points and keep calculating it, because that defeat the purpose of showing the utility of the method, but it is best done using a computer programming and writing down either a code or using some softwares for the fitting part. But if you use a software instead of writing a program, you should still know that what are the methods that the software is using. The software is made by human beings, and since the human beings have to follow certain algorithm, one needs to know that what are the algorithms that have been followed. So, and let us just start with a little bit of mathematical preliminaries. We will not talk much, mostly we will talk about the linear regression methods and how we can talk about even just for a linear fitting, how can we sort of take into account the errors that are that could arise from a set of data points. So, in this, as I told, let us talk about a few key statistical concepts Let us talk about normal distribution, and let us talk about the linear regression. So, if we agree on this, then the simple statistical concepts which you already are aware of, I am just reminding you. Your engineering economics course or your steam tables in thermodynamics course, or if you are a teacher and dealing with a class of a large number of students, the marks etc., they all require certain amount of statistical analysis. And the reason that it is required is that you need to show either your teacher or your evaluator or your the head of the department that how your performance in teaching was. And in order to do that, there has to be some quantitative aspects of teaching, and the quantitative aspects are that what is the average or what is the mean. Same goes for any other data set that you are talking about. Maybe you are calculating a few something relevant in a particular physics experiment, or you are doing some chemistry experiments and you have generated a table, and you need to know a few things, and those few things, the first one starts with an arithmetic mean, which is the easiest. And the arithmetic mean is defined as x bar, which is equal to I equal to 1 to n x I divided by n. And we have so this is the mean of n data points. We have taken just the arithmetic mean, that is we have summed them up and divided by the number of data points. This of course causes no or rather this involves no biasing of data points, because in some experiments or in some measurements, there could be certain amount of data are more relevant than others, and then you need to weight that data point. Weight means attach a certain larger weight to those data points which are of importance, more importance than the others, and this is called as a stochastic sampling, or rather they have different names in a particular context, but we are simply talking about the arithmetic mean. And we can also talk about the standard deviation, which is an important quantity by itself. Why standard deviation important is that if the deviation is large from the mean value, then of course, the data are too scattered. Say the marks of a particular class of students in a given course, if they are distributed over very large number of values, then one has to understand that there are really some very good students and some poor students in the class, and that causes a large discrepancy of values. But if you have if you have a distribution, or if you have a standard deviation that is low, which means that more or less the students have gotten numbers or marks which are close to the mean value, which means that there is on an average the teacher has done well. So, this is defined as say S x is equal to S t divided by n minus 1, where S t is equal to the quadratic from the mean value, the difference, the square of the difference of each of those data points from the mean value. And so, this is the standard deviation, and sometimes we actually talk about the square of this, because there are square roots involved, and when you take square roots there are further errors that could be introduced. So, these are removed when you talk about a variance, which is simply S x square, which is equal to sum over I x I minus x bar square divided by n plus n minus 1. So, that is the variance that we often talk about. Okay. There is also another thing that is said, it is called coefficient of variation. And one writes a CV for that. So, a CV is defined as Sx, which is defined here as the standard deviation, divided by the mean, and then you take the percentage of that. That is called coefficient of variation. And so, in principle you should take a set of data points, which could be anything. You will find a large number of data points which could be leading to, I mean, which could be, you will find it in internet that it is about results of an election, or the coefficient of linear coefficient of expansion of solids or metals, or it could be the steam tables in thermodynamics, as I told, or this could be anything, marks obtained in a 101 course in a university, and various number of things. So, one can calculate these all these quantities and understand what those set of data points mean. Next, let us talk about a normal distribution. And this normal distribution is nothing but when you have a set of data, the distribution of the data is important. As I told, that we need to understand what is the distribution of such a data point. Is this data point centered about certain things, or there are bimodal distributions, that is they are centered about two such values, and so on. So, let us just talk about just what they are centered about one value. And what one can do is that let us say you have a class of maybe 500 students, and they have the maths marks are out, and it is put on a sheet of paper, and one is given the task to analyze that. So, what you can do is that one can make bins of how many people got 0 to 10, how many people got 10 to 20, how many people got 20 to 30, and 30 to 40, and so on, 50, 60, 70, 80, 90, and 100. It usually happens that there are very few very poor students and very good very few say excellent students, who are really very good. So, one can actually get a distribution which is like this, and so on, and just drawing and it starts speaking about certain value, and then of course, these are what I am drawing is just a freehand histogram, okay, and this. Okay. So, it is like this. So, if the data points, if the number of students are very large in a given class, then you can actually discretize it even smaller bins, that is 0 to 5 marks and 5 to 10 marks and so on, and then eventually you land up with a distribution. So, we are talking about a distribution like this. Now, if this distribution is like this, that is it has a mean and it has a kind of variance, then this has a name, it is like a bell shaped curve. Pretty much what I wanted to draw here, that is one would be termed as a very good teacher if it is really a sharp bell, because if the the average is quite high and most of the students have gotten values near the average, and there are very few people who have got very low values or almost none, and similarly maybe the values which are like the marks such as 100 etcetera, or close to 100, maybe there are only few people or there are none, but even then one is termed as a good teacher if the majority of the students have done in the say average or above average range. So, this is called as the normal distribution. Now, it is in fact one can test it that so if a set of data is normally distributed, normally means there is no abnormal there, but if this follows a normal distribution, then distributed, then the range defined by x bar minus S x, we have defined S x here, which is the standard deviation. So, it is on either side, on the left side or the lower side of the average value and the right side of the average value. So, this contain something like 68% of the data, of the total number of data, okay, if it is a normal thing. And between x bar minus 2 S x to S bar, sorry, not S bar, it is x bar plus 2 S x, we have contain 95% of the data. Okay. And of course, there are deviations from that. There could be deviations like the one that I have drawn is that there is this is called as a Lorentzian curve, which has a bigger tail towards lower values, and it is slightly skewed towards or rather this is not like exactly a normal curve, but it is a curve that is skewed towards one side, that is towards the larger values and so on. And so, these are the data points that we actually talk about in experiments. There is also a Gaussian distribution, but the Gaussian distribution corresponds to which spreads from x equal to minus infinity to x equal to plus infinity, if you are talking about centered about 0. But in real experiments we cannot have values extending up to plus minus infinity, but of course, we can talk about suppose we talk about velocities of molecules in an ideal gas. So, there is the velocities can actually go from minus infinity to plus infinity. If you remember Maxwell-Boltzmann distribution and calculation of the average velocities and the root mean square velocities, we have actually integrated from minus infinity to plus infinity for the velocities, which means they can, there is equal probability for them to go to minus take values minus infinity to plus infinity on either sides. So, those are called Gaussian distributions. So, we let us pause here for a moment and we will carry on with the linear regression and maybe some more better approximations than that in order to fit our data. But the ones that we have talked about, that is the Lagrange's interpolation formula and the Newton's interpolation formula or the polynomials that we have talked about in that connection, these work pretty well for fitting large number of data points.